Hello there, and welcome back to this series on elementary probability and statistics. In the last couple of videos, we've introduced some of the basic principles associated to statistics, in particular samples, populations, statistics, parameters, and a couple of the metrics that we use for measures of central tendency. In this video, we're going to be focusing on another measure, in particular the measures of position, that can tell you where a particular element is with respect to the other elements. So let's start off with a general set. Let's call this set S, and let's call its elements x1, x2, all the way out to xn. And let's assume that this set is ordered. Some people will also say that this set is ranked. And when we say that the set is ranked, this means that x1 is less than or equal to x2 is less than or equal to all the way down to the last element xm. So we call x1 the minimal element of S and xn the maximal element of S, assuming that these elements are listed from least to greatest. So the easiest measures of position that we can define are the minimum of S, so that's going to be equal to x1, and the maximum element of S, which is going to be equal to xm. So of course we probably already know these particular measures of position, but we're going to actually be using these in quite a few calculations for a couple other measures as well. But the first measure of position that's a little different than these two is what we call percentiles. So let's give a starting definition. This isn't going to be the final definition we're going to have, so I'm just going to call it a starting definition because I want you to sort of think about this definition as I sort of go through the derivation of it. And this is going to be the definition of a percentile. So we're going to define the pth percentile. And when I say the pth percentile, I mean like the first percentile, second percentile, 34th percentile, 100th percentile, something like that. And we're going to be denoting it by x sub p percent. So p percent is a subscript for x. And this is going to be the smallest ranked element of S such that some people will abbreviate such that as s dot t dot, just to save some room, that p percent of the data is less than or equal to this number xp percent. And here this number, p, must lie in the continuous interval 0 to 100, not including 0, but including 100. So there is not going to be a 0th percentile, but there will be a first percentile up through a 100th percentile, and all decimals in between. So from this definition, you should be able to see that the 100th percentile is always going to be equal to xn. And this is for all non-empty sets S. And you may see people write this this statement for all non-empty sets as upside down A, S not equal to the empty set. That's just set notation for the same exact thing. And why do we say that xn is the 100th percentile of the set? Because 100% of the data is less than or equal to the maximal element of the set by construction, right? So that is the basic definition of percentiles. Now let's work through how we can derive like a formula for all the percentiles that are less than 100%. Okay, so let's just look at a basic example to sort of guide us in our investigation. So let's create a very small set. Let's let it be 3, 7, 10, and 20. And this set is obviously already ranked. So therefore this is going to be x1, x2, x3, and x4. So as we can see, 25% of the data is less than or equal to 3. We see 50% of the data is less than or equal to 7. We see that 75% of the data is less than or equal to 10. And finally, we see 100% of the data is less than or equal to 20. So we can at least start talking about quartiles, maybe in some sense of the word. So x 25%, so this is going to be the 25th percentile. So the 25th percentile. Now, this is not to be considered totally with quartiles, but percentiles can be used to define quartiles because percentiles are actually pretty easy to calculate. But we see that from this example, the 25th percentile is going to be equal to 3. The 50th percentile is going to be equal to 7. The 75th percentile is going to be equal to 10, and trivially, the 100th percentile is going to be the maximal element of the set, and that's going to be 20. Now, also keep in mind that the 50th percentile is not necessarily the median, but one could define the median in terms of percentiles from this particular perspective, right? But of course, you'll get conflicting answers. For example, the median, the traditional median would be the average of 7 and 10, which is definitely not equal to 7. But it can give you some sense of how there can be different perspectives of what do you mean by, percentiles and quartiles and positions with respect to each other, because there's different ways to sort of view the world, right? So of course these are very trivial to see, but what about an arbitrary set? Maybe it's not a pretty set, and maybe the percentages that we're looking for aren't exactly quarters or tenths or a pretty number like 5 or something like that. So let's assume we have our spectrum of our set S, and let's look at it from a number line perspective. So our 25th percentile corresponds to x1, our 50th percentile corresponds to x2, our 75th percentile corresponds to x3, and our x4 corresponds to our 100%. And our 0% is chilling down here, but of course he's not associated to a value, as mentioned before. Because if there was such a thing as a 0 percentile, that means there's an element corresponding to that, but an element always is a percentage of the entire set, so there can't be a 0 percentile, at least by this definition. So let's ask a question. What about the 60th percentile? So what would the 60th percentile be? Well, is it going to be x1? Well, 60% of the data definitely is not less than or equal to x1, only that value is less than or equal to that, and that's definitely not 60%. And if we consider x2, well, that's not going to be a 60th percentile either, because only 50% of the data is going to be less than it. Now, x3 is a qualified candidate because 60% or less than the data is less than or equal to that, in particular 75%. If there was a data value somewhere in between here, if we were to create a continuum of values, then the 60th percentile would be somewhere in the middle of that, right? But if we were to assign a percentile element to the 60th percentile rank, then x3 is the only likely contender. And you may ask, well, what about x4? Isn't 60% or less than the data less than or equal to x4? And the answer is yes. But remember how we defined the percentile. It is the smallest ranked element of S such that that particular percentage is true, right? And clearly by this construction, since this is a ranked set, x3 is less than or equal to x4, therefore x3 would be the 60th percentile of this particular set. In particular, x3 is the 51st, 52nd, 53rd, 54th, 66.7th, 74th, and 75th percentile, all in one. So usually percentiles are not usually used for samples that only have 4 elements. Usually percentiles only really make sense when your data set has at least, let's say 100 elements. Therefore you have 1 element for each percent, right? So it's usually more useful there, usually not used for smaller numbers, but we usually use smaller sets to help us gain an idea of how to calculate these particular elements. All right, so in particular, how can we gain, for example, for our particular example, the size of the set was equal to 4, and we were able to calculate, okay, well, this is the 60th percentile, so p is equal to 60%. Is it possible that we can get from the sample size n and the value of p to get this particular index 3 associated to the percentile element that we are searching for? And the answer is yes. So maybe we can just play around with the number 60% in 4, and maybe we can get something here. So notice that 60% of 4, our sample size, so that's P, and that's going to be M, this is going to be equal to 2.4. So how can we get to 3 from 2.4? Well, we can round up to 3, right? So notice we are not rounding in the traditional sense of the word because 2.4 rounds down to 2 because 4 is less than 5. But if we round up, just a hard round up, regardless of what that number is, we actually will always get this particular element from this definition. And we usually write this roundup element via a ceiling notation. So we write 60 divided by 100, so that's our p value. And then 4, that's going to be our n value. So that means round up. Some people call it ceiling. So when you see this little notation, this corresponds to round up, and similarly there's another notation. This means round down. Some will call this the ceiling function, some will call this the floor function for obvious reasons, and we can clearly see that this is going to be equal to the ceiling of 2.4, which is going to be equal to 3, and there's no bottom side of that bracket. Okay, so now we have a proposed formula for calculating percentiles, and this is actually how we're going to define a percentile, at least from the formal definition of the word. All right, so definition. So the pth percentile of an ordered set S with the size of S equals to n is the element xk, which must be an element of S, such that its index k is equal to the ceiling of p divided by 100 times n. That looks like a weird symbol, right? So there we go. And that is the formula for the percentile. Now keep in mind, some people may define percentiles a little bit differently than this. Some people might round it down. Of course, the definition will be slightly different, but this is one reasonable definition for percentiles that I find at least makes sense, and here's a nice little explanation for it. So now that we have some definition of percentiles, let us go through an example and also talk about other measures of position that people may decide to use. Alright, suppose we have this set S, and it's defined to be the set of elements 32, 14, 15, 26, 7, 3, 10, 30, and 17. What would be the 45th percentile of this data set? So the first thing that we would have to do is find out the index associated to the rank for the 45th percentile. So the first thing we would have to do is figure out, okay, what is the sample size equal to? So we should be able to see that we have 3, 6, 9 elements in this particular data set. So this means what? That means the index associated to the 45th percentile is going to be equal to the ceiling of 45 divided by 100 times the sample size 9. So that's going to be equal to the ceiling of 4.05, which is going to be equal to 5. Keep in mind, ceiling just means round up and nothing more. Now, in order to find the element associated to this particular rank index, we need to rank our particular set from least to greatest. So first off, let's find the minimal element. So that's going to be equal to 3, followed by 7, 10, 14, 15, 17, 26, 30, and 32. And of course, make sure you have all your elements so you're not missing anything. So we have 3, we have 7, we have 10, we have 14, we have 15, we have 17, we have 26, we have 30, and we have 32. So we have all of our elements accounted for. So that's wonderful. And make sure they're listed from least to greatest, of course. So this is going to be x1, x2, x3, x4, and this right here is going to correspond to x5. So that means the 45th percentile, which is going to be x5, is going to be equal to 15. So that means 45% or less of the data should be less than or equal to this number. right? And you should be able to verify that that is indeed the case. So let us talk about a couple other percentiles um, that may be used in your daily practice of statistics. So the next thing we're going to talk about is quartiles. And quartiles can be a little bit tricky only because some people use them and define them a little bit differently, similar to how we define percentiles a little bit differently than some other people. But one thing is in common with all the approaches, and those are the extreme quartiles. We're going to call them Q0. This is always defined to be equal to the minimum of S, and Q4, this is always going to be defined to be equal to the maximal element of S. So if we have a data set and we chop it up into 4 regions, we're always going to have 5 elements. Well, that's 3 sets, right? So there should be another region here. So if we have 4 regions, so region 1, region 2, region 3, and region 4, then there should be 5 elements, Q0, Q1, Q2, Q3, and Q4, that is going to define those 4 regions, right? So there's always n plus 1 points that create n subintervals. If you're familiar with calculus and Riemann sums, that's a common concept that is usually introduced. So also keep in mind that Q4 is always going to be the 100th percentile, so there is a little bit of consistency here. But we call Q0 the 0th quartile and Q4 to be the 4th quartile. So how would we define the other quartiles, Q1, Q2, and Q3? So there's going to be 2 variations for this, and we're going to call this the center quartile. So the center quartile is most of the time taken to be the median of S. Or another variation that you could define Q2 to be, you could define Q2 to be equal to the 50th percentile, which is going to be equal to, so what is that going to be? So that's going to be equal to 50 divided by 100 times n, or n divided by 2. Nice little formula for the median, right? But keep in mind, the median is not always, but sometimes is equal to that. But most of the time in literature and textbooks, we usually use Q2 to be equal to the center quartile. But there are some variations that may prove more useful or more practical for your particular study. But so you should always be aware of some alternatives that you could use. So that's the center quartile. So what about Q1 and Q3? So those are what we usually call the inner quartiles. So the inner quartiles. So this is Q1 and Q3. So I'm just going to define these. So Q1 and Q3. This is going to be the median of SL. And this is going to be the median of SR. And you might be thinking, well, what's SL and SR? We haven't defined those particular sets. Well, I'll introduce them in just a moment. But there is, of course, the alternative using percentiles. You could define Q1 to be equal to the 25th percentile. So that's going to be equal to 1/4 of n, the saline. And Q3 is going to be equal to the 75th percentile, or 3/4 of n raised up. Right? So these are the percentile-based versions of quartiles or inner quartiles. But again, most of the time, when you see like textbooks and stuff, at least in the present day, they usually use medians or median-based approach for interquartiles. All right, so how can we calculate the inner quartiles? Let's go through a couple examples. And there are actually 2 variations that you need to be aware of. They are called inclusive versus exclusive inner quartiles. But for odd n, there is usually no difference. And let's go through a couple examples because we're actually introducing a few new concepts here. SL, SR, inclusive versus exclusive. So it's just easier just to talk about an example to sort of get an idea of what's going on here. So let's consider the even case first. So 1, 2, 3, 4, 5, and 6. All right, so this is going to be Q0, this is going to be Q4, And the median, Q2, is going to be equal to the median of this data set, so that's going to be 3.5. So we're going to be using the median-based approach for center quartiles and inner quartiles. Now notice when I draw this red line, notice I've broken up the set into two evenly sized sets. So this set right here is I'm going to call SL. So SL is going to be equal to the set 1, 2, and 3. And this set over here, I'm going to call this SR. So SR is going to be the set 4, 5, and 6. So notice that this approach is very easy if the cardinality of the set is even, right? Because the median is always, can chop the set in half. So this right here is the median of SL, so this is going to be Q1, and this is the median of SR, this is going to be Q3. So when the cardinality of a set is even, the median-based center and inner quartiles are actually very easy to calculate. So the inclusive and versus exclusive does not apply to even sized sets. The inclusive versus exclusive only applies to the odd case, and I'll show you why it needs to be considered in that way. So let's consider that. So example 2. So let's consider another basic set. Let's do 1, 2, 3, 4, 5, 6, and 7. So notice here that the median is going to be 4, right? So of course this is my Q0, that is my Q4, and 4 is my Q2, if we're using median-based inner quartiles and center quartiles. So there's two ways that one could partition this set. So one could look at 1, 2, 3. One could look at 4, 5, 6. So this type of partition, so S is equal to 1, 2, 3, union 4, union 5, 6, and 7. This is what we refer to as the exclusive approach. Now, why do we call it the exclusive approach? Because we're not including the median in the left or the right. So that's one version. Or you could include the 4 in the left and the right. So for example, you can represent S as 1, 2, 3, and 4. Union 4, 5, 6, and 7. Keep in mind the union is still the original set. So this is going to be the inclusive approach because we're including the median in both the left and the right. Now, of course, the inner quartiles from the definitions of SL and SR are going to be slightly different, exclusive versus inclusive, but the way to find those inner quartiles is going to be the same for both, right? So this is going to be SL, this is going to be SR for the exclusive approach. So that means the inner quartiles are going to be equal to 2, the median of that one, and Q3 is going to be the median of the right-hand side, so that's going to be 6 for the exclusive approach. And if we go over to the inclusive approach, the median of the left-hand side, so this is going to be SL, is going to be the average of 2 and 3. So Q1 is going to be equal to 2.5, and Q3 is going to be the average of the middle two of SR, so that's going to be equal to 5.5. So those are the exclusive versus inclusive, which matters only if the cardinality of the set is odd. When the cardinality of the set is even, exclusive and inclusive give you the same answer because there's no distinguishability between the two. All right, so that is the inclusive versus exclusive approaches for finding inner quartiles and also center quartiles. But keep in mind, if you are using percentiles to define center and inner quartiles, you actually don't need to worry about this exclusive, inclusive, and partitioning approach to these things. So that's one thing to keep in mind when you want to decide which metric to use. All right, so there's one more thing that I want to mention about quartiles, and that is one of the graphical approaches to data that is directly tied to quartiles and such. So you may have heard of box and whisker plots, but the formal name is just box plots. So if you have a set of data, and let's assume this is for example, the real line. So it goes from, for example, minus infinity to positive infinity. So the box plot representation for a set of data usually looks something like this, right? So this could be -10, this could be 52, this could be 36, this could be 27, and this could be, I don't know, 41. So this element corresponds to Q0, this element corresponds to Q4, this element corresponds to Q1, this element corresponds to Q3, and this element corresponds to the median Q2. You may see some software put a little X here. The X is typically going to be associated to the median. So if this is 38, for example, then this corresponds to the arithmetic mean or average of the data set. So this is a box plot representation, which sort of mixes uh, measures of positions and also measures of central tendency into one representation. Also, you may see some other types of shapes chilling out here. For example, these little circles or dots, some people will use X's, but I don't like X's for the mean and X's for these things. So usually these elements here are going to be represented as outliers. And how we can identify an element as a potential outlier is another discussion that we're going to go into when we go into talking about measures of variation in a little bit more detail. But I just wanted to mention this box plot representation for data because it's directly associated to quartiles, right? So that's great. So let's just briefly summarize a couple of the things that we've discussed in terms of measures of position. So the probably most difficult thing that we talked about, at least today, would be quartiles, and we have two variations for this. So the easiest to calculate probably would be the percentile approach, right? So the percentile approach is easy to calculate. So it's easy to calculate, but it can be sometimes gives misleading results. So it sometimes gives misleading results. And you would have to go through several different examples to sort of convince yourself of this. But for now, I'm just going to leave it at that particular thing. But it's sort of tied to how percentages change dramatically when you slightly change the data. For example, if you have two elements and you're the minimum, then you're a 25th percentile. But if you introduce a third element that's greater than that, then now you're at the 33rd percentile. So you've changed from 25 to 33. So that's a change of 8% just by introducing one element. So those are one of the issues with percentages, which is why percentile approaches for interquartiles and centerquartiles aren't usually used. But the median approach is of course the industry standard, and of course we have two variations of it for the odd case, and that would be the inclusive versus exclusive approach for median-based quartiles. And this is more tedious to calculate, obviously, because you have to partition, you have to rank, and everything like that. But it's more reliable in terms of interpretations. So those are some of the things associated to quartiles that you definitely should be aware of. And let's also summarize the measures of positions as a whole while we're at it. So measures of position. So the very first measures of position that we discussed was the minimum and the maximum. The second was the median, right, which is the center quartile for a data set. And then we talked about percentiles and quartiles. So keep in mind the first quartile, Q1, is not necessarily equal to the 25th percentile. Similar for the 50th percentile in the median, the 75th percentile in Q3. They're not always necessarily equal to each other, even though both of the words end in the word tile. A fourth measure of position is difference scores. Difference scores. And what difference scores represent is the relative position position, not necessarily with respect to the order, but with respect to a measure, that M looks a little funny. So a measure of central tendency. Typically the mean, the arithmetic mean, and of course sometimes the median as well. So we define the difference score for a particular x value, and I'm going to represent that by dx. This is going to be equal to the distance from x minus mu, so this is for populations. And dx is going to be equal to x minus x bar, and this is of course for samples. Okay, so these are the two variations for difference scores. So if you have a value that is larger than the mean, the difference score is going to be positive. If you have a difference score, if you have a value that is less than the mean, then the difference score is going to be negative. And there's a couple things that we can sort of summarize here. So if the difference score is greater than 0, that means x is to the right of or is greater than the mean or median if you so choose to do so. If the difference score is less than 0, that means x is to the left of the mean or the median. And you can probably guess if dx is equal to 0, that means x is the mean or the measure of central tendency that you are comparing to. Now keep in mind the difference score could be positive or negative, so there's a couple things that we can say about the size. If the magnitude of dx, or the absolute value, is significantly greater than 0, that is, it is a really negative number or a really positively large number, this means that x is far from, of course a subjective term, far from the mean. And what is the opposite of if the size of dx is really greater than 0? The opposite of that statement is the absolute value is approximately equal to 0. That means x is really close, again a subjective description, to the mean. Right? And of course, keep in mind you could choose the median, you could choose the mid-range, you could choose the mode, you could choose any measure of central tendency. Of course, that goes into more complex metrics, but regardless, these are all measures of positions because we're comparing a particular value and how far it is and where it is with respect to another number, or possibly even a set of numbers as well. So this is the measures of position and the metrics we commonly use for that. Last video we talked about the measures of central tendency. In the next video we will conclude with our most common measures and metrics with the measures of variation and dispersion, which talk about how data is spread or compact with respect to the entire data set. So I look forward to seeing you all there, and I hope you all have a wonderful day. Take care.